This is the circuit called the potentiometer circuit. We'll use it to find the internal resistance as well as the electromotive force of an unknown battery. Now in this circuit, notice that the main battery is going to be output number 1 of the interface. The galvanometer will be replaced by the current sensor. The unknown battery is going to be a D-size battery, under which we have also the resistance box. Between point A and B, this red wire is called the slide wire of the potentiometer, and it has a length of 1 meter. In this experiment, changing the resistance box to a given values, for each value we'll be looking for the balance point, which is point C in this diagram. Now the balance point is the point at which the galvanometer reading is 0. And when this occurs, then the current through this branch is going to be 0. And this only occurs when balance condition is satisfied. Now when the current through this branch is 0, this means that the voltage difference between points A and C is equal to the voltage difference across the unknown battery, or the voltage difference between these 2 points. And since there is no current in the circuit, then this voltage difference is equal to the EMF of the battery. Starting with the condition that says that VAC is equal to the voltage difference across the battery, this is the first step in the derivation of the equation of this experiment. Now the equation is shown here on the right side. And after you get the data for this experiment, you will plot 1 over R on the y-axis and 1 over L on the x-axis. Let's look at the variables that we have in the equation and make sure that we understand everything. Now uppercase R is the value of the resistance box. L naught is the total length of the wire, which is, as we said, 1 meter. E in the equation is the EMF of the unknown battery. VAB is the voltage difference between points A and B in the circuit diagram. And lowercase r is the internal resistance of the unknown battery. L is the length at which the balance condition occurs. And lowercase r is repeated again, which is again the internal resistance of the battery. Now notice that L naught, E, VAB, and lowercase r are all constants in this experiment. So 1 over r is on the y-axis, so all of this is going to be your variable on the y-axis. 1 over L is on the x-axis, so this is the x. And as we said, all of these are constants. 1 over R, once again, is a constant. Let's call it B. So the equation looks like y equals a constant times x minus b, which is the equation of a straight line that has a negative y-intercept. So we expect our relation to look like this. So it's a straight line with a negative y-intercept. Notice that the internal resistance is equal to 1 over the y-intercept. Make sure that at the end you get a positive number of the internal resistance. There is no negative resistance. Once you get lowercase r, which is the internal resistance of the battery, from the y-intercept, then you can use the slope to find the EMF of the battery, because remember that the slope is equal to L naught E over VAB times R. So you plug all the values here to find the EMF of the unknown battery. Now, VAB is the voltage difference between points A and B. And to find the voltage difference between points A and B, you are instructed to use a high impedance voltmeter to do this. In our case, we will use the voltage sensor, which has high impedance. The reason why we should use a voltmeter with high impedance is that you don't want any current to pass through the voltmeter. So for example, let's take a look at this simple circuit. And let's say that this is a resistance that has current I in it. And assume that you use a low impedance voltmeter to measure its voltage difference. So this is a part of a circuit. High impedance means high internal resistance of this device. So if this device has low impedance, this means that a large portion of the current will pass through it. And the remaining current will pass through the resistor R. So if the voltmeter has low impedance, it's going to change the current that passes through our resistance in this example. So we have to use high impedance voltmeter in order for this current I1 to be a very small number. Because remember, always the meter should not change the characteristics of your original circuit.
So here is the circuit diagram for this experiment. To make things easy for ourselves, we will divide this circuit into two. So we will connect the upper part of the circuit and then we will join it with the lower part. The positive side of the battery is connected to point A and the negative side is connected to point B. So here is the positive side of our battery. Let's take a wire and connect it to point A, which is according to our diagram on the left side of the slide wire. The negative side of the battery is connected to part B, which is the right side of the slide wire. So we're done with the upper part of the circuit. Now for the lower part, notice that we have the resistance box connected in parallel with the unknown battery. So this EMF and internal resistance are both of them for the unknown battery, which is the D-size battery that we have right here. According to the diagram, the positive side of this battery is connected to the left side of the resistance box. So let's look for the positive side, which is here, plus. We have a plus sign. So this should go to this side of the resistance box. And the negative side is connected to the right side of the resistance box. So this is the lower part of the circuit. Now notice that the positive side of the unknown battery and the positive side of the main battery are all on the same side, okay? And they are connected together using this wire, okay? So this wire connects point A to the positive side of the unknown battery. So we will take a wire between point A and can move things around this point right here. Now the other side, according to our diagram, is connected to the galvanometer and the other side of the galvanometer connected to the pointer. So remember that in this experiment we'll replace the galvanometer with the current sensor. So one side of the current sensor is connected to the negative side of the unknown battery. And the other side is connected to the pointer. Now this is the pointer for this experiment. It is flat so that you have good connection with the slide wire. And for this one, it is open. This is how it is. So it has a very strong connection. So you simply push it hard and it will enter its hole. Okay. Now make sure that everything is sorted out correctly away from our working area. Just like this. This is your working area. So the only thing we have is this wire right here. Now this is the resistance box and it is very important to learn how to use it before you start the experiment because you have to do your experiment quickly. Now this knob here, it has times 1 ohm beneath it, which means that these numbers represents how many ohms you have. So for example, if I set this to 5 times 1, that's 5 ohms. Now, this is correct provided everything else is set to 0. Now, if I have this set to 1, the second knob, 1 times 10 is 10. So 10 plus 5, we have a total of 15 ohms, and so on. So all the contributions of these knobs add up like this. To start our experiment, we have to set this to 5 ohms and everything to 0. Also, there is an important point to notice here. This battery is connected directly with the resistance box. So once you connect it, you start having current flowing in this portion of the circuit. Now this current, what it does is that it heats up this portion of the circuit. Also, it will reduce the EMF because it's going to discharge over time, especially if it was a weak battery. So to prevent any error caused by this, you have to take your readings very quickly. So I'm going to demonstrate here how to take your readings. First, after you connect everything, you start your program so that you have a 2-volt voltage difference here. And then you touch one side of the slide wire with the pointer. Then touch the other side. One side should give you a positive reading and the other side should give you a negative reading, which means that there is a point in between that has a current of 0 amperes. Okay. Now, once you are ready and you are satisfied with your circuit, then you can start changing your resistance. So for example, I have this set to 5 ohms. So I'm going to slide the pointer along the wire until I see a reading of 0 amperes. Once I get this reading, I can take the length of the reading from here. Then once I get this reading, I'm going to change to 7 ohms and then slide from this point on. You don't have to start from the beginning because the new balance point will be after this. So start from here and search for the new balance point. Then change to 9 ohms on the resistance box, find the new point, and so on. So all of your readings shouldn't need more than 1 minute worth of data taking. Because remember, otherwise you start having errors because of this problem. And there is also another problem, which is this wire is connected to 2 volts all the time. So it's going to heat up, and also you'll notice that if you leave it for a long time, you'll notice that because of heat, the length of the wire increases as well. Okay. So to prevent all of this, you have to take your readings quickly in the way I just demonstrated.
We will add a current sensor to channel A, because remember we replaced the galvanometer with a current sensor. And we will add the internal voltage current sensor so that we can measure the voltage difference between points A and B. Now for the signal generator, we want output 1 to be a DC signal of 2 volts voltage difference. And let's set this to auto. Furthermore, we want to change the mode of data from continuous to fast monitor mode. And also we will add a digital display, one for the current and one for the voltage. So this will display the reading of the current sensor, and this one will display the voltage VAB. Which should be constant throughout the experiment. So let's make this a small display so that you don't get them mixed up. And now we are ready to start taking the data. So we have the resistance box set to 5 ohms. And let me click on monitor. Now we will touch both sides of the slide wire. One side should give positive reading and the other one should give a negative reading, which means that there is 0 in between. So our circuit is correct and functional. So now we will start sliding the pointer along the slide wire to search for the balance point when the resistance box is set to 5 ohms.
Okay. So here we have the resistance box set to 5 ohms. So I'm going to scan quickly while watching the screen there. Now notice if the pointer slides off the wire, I also get something very close to 0. So you have to pay attention to this. You have to make sure that the pointer is actually touching the wire and you're having a 0 at the same time. Here is the first reading. Okay. Now notice we have 2 scales. Now if you compare this to our previous diagram, you'll notice that L is measured from the left side to the balance point. So for this reason, we have to use the upper scale of this measure. So again, here is the first reading, which occurs right here. Okay. Now it took me too long, but it has to be done quicker than this. Now go to 7 ohms and then find the new balance point. Here's the new balance point. Okay. Now I'm going to go to 9 ohms and find the new one, which is right here. Go to 11 ohms, which is 1 plus 1 on the tens, and here's the new balance point. Now let's go to 13 ohms, and here is the new one. Now let's go to 15, and here is the new balance point.